Hello class, today's lesson is 5-2 in your textbook, and it's all about how to use perpendicular bisectors. So we've seen what bisectors are before. Sometimes it's been a segment bisector or an angle bisector, and now a perpendicular bisector can be a segment or a ray, a line, or even a plane that is perpendicular to a segment at its midpoint. So perpendicular bisector can be any one of those four things. And if I have this segment AB right here with P being its midpoint, the only difference between a perpendicular bisector and any other bisector is that when it is drawn, it meets at 90 degrees. So for instance, I have a line here, CP, which is bisecting AB at 90 degrees, so it is a perpendicular bisector. Okay? So our first theorem is titled 5-2, the perpendicular bisector theorem. And it says, if a point is on the perpendicular bisector of a segment, so already I'm given that this is the perpendicular bisector and point C is on it, then that point is equidistant from the endpoints of the segment, which means from C back to point A, and then also from C to point B, that those two distances are exactly the same. That's what equidistant means. So, if CP is the perpendicular bisector of segment AB, then CA, that length, is equal to the length of CB. That's what our theorem 5-2 is telling us. And there's a converse to this theorem. The converse is theorem 5-3, and it's the converse of the perpendicular bisector theorem, and it says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of that segment. So down below I kind of have the same diagram, but I have this extra point D, okay? And so what it's saying is that if this point is equidistant from A and B, so if I draw this in the diagram, this distance and this one, if those two points, or I'm sorry, if those two segments are exactly the same, then D must be on this perpendicular bisector of CP. So let me write this down. If DA is equal to DB when it's measured, then D lies on the perpendicular bisector. In this case, we're just going to say the perpendicular bisector of AB. Okay, so there we go. I have two theorems to get me going in this section. So let's go ahead and do an example. Our first example already tells us that BD, that line, is the perpendicular bisector of AC, of this segment right here. And all it wants me to do is to find AD. Well, because I just have those two theorems, I know that AD, since D is on the BD bisector, then AD must be equal to CD. So I'm going to write that down. That AD is equal to CD. And AD, as I can tell, is 5x. And CD is 3x plus 14. So I'm going to move the x's to the same side. So 2x is equal to 14. So then I find that x is equal to 7 when I divide both sides by 2. Okay. If I simply plug it back in now, AD is 5x, so that means 5 times 7, which is 35. There we go. I found the length of A to D. Okay. Our next example is a little similar. Okay. And it's kind of two-parted. This time I have this diagram and it's telling me that WX, that line right here, is the perpendicular bisector of this segment Y to Z. And all it is asking me at the beginning is what segment lengths are equal. So since I know it's a bisector, that's automatically telling me that YX is equal to ZX. Okay, that's kind of a given knowing that it's a bisector. Also, I know from Theorem 5-2 that YW is equal to ZW. YW is equal to ZW. This is by Theorem 5-2. And then also, just by looking at the diagram, since YV is 25 and also ZV is 25, those segments must also be equal to one another. So YV is also equal to ZV, and that's by just shown in the diagram. I'll just say in diagram. So I have three sets of segments that are equal to one another. The second part is just asking me simply, is the point V on the line WX, which is my perpendicular bisector? And I can say since V is equidistant from Y and from Z, then I do know that YV is equal to ZV as well. Okay, then I can say that V is on WX by the converse of the perpendicular bisector theorem. So yes, it is going to be on that line. That's kind of all that we're doing with these diagrams. So now I'm just going to introduce you to something else, okay? And it says, when three or more lines, rays, or segments intersect at the same point, that point we're going to call the point of concurrency, they are called concurrent lines, rays, or segments. Okay, so when three lines, rays, or segments meet together at this special point called the point of concurrency, they are all concurrent with one another. So that's going to help us out with our next theorem. It's Theorem 5-4, and it's called the concurrency of perpendicular bisectors of a triangle. Okay, so we're going to find three different perpendicular bisectors in a triangle. And it says, the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. That's pretty cool. Okay, so let me show you a diagram right here. Okay, and I've already drawn this triangle ABC. And I went ahead and I found the perpendicular bisector of AC, which was this point F. It was going up at 90 degrees and it was right in the middle, okay? And then I also found the midpoint of AB, which is at D, and I drew that perpendicular bisector. And then I also found the midpoint of BC, right here at E, and I drew the perpendicular bisector right there. So what this theorem is telling us now is that the distance from each vertice to that point of concurrency right in the middle, where all three of them are meeting, so this distance right here, and this distance from B to that point, and the distance from C to that point, should all be the exact same distance. So we're going to call this point P right here. If PD, PE, and PF are perpendicular bisectors, then PA is equal to PB, which is equal to PC. Okay, so if I know that these three little segments are perpendicular bisectors, then these purple segments are all the same length. Pretty cool, right? So the very final thing that I'm going to introduce is called a circumcenter. And it says that the point of concurrency of the three perpendicular bisectors of any triangle is called the circumcenter. Okay, so there's different types of triangles, right? The first triangle is kind of the one that we just had. It was an acute triangle. And if I put this inside of a circle, okay, and I have an acute triangle, as you can see right here, I already drew all three of the perpendicular bisectors of each of the sides of the triangle. And where they meet is inside of this triangle. So that point P, that circumcenter, is inside the triangle. Okay. I also have a right triangle that I drew for you inside of a circle. And this time I drew this perpendicular bisector of this left-hand side. I also drew the perpendicular bisector of the base right here. And I drew the perpendicular bisector of the hypotenuse. And as you can see, actually, this time the circumcenter is right on the triangle. It's on the side of the triangle. So this time P is on the triangle. It's just a very cool fact. Okay. The last one that I have is an obtuse triangle. Okay, I just drew any random obtuse triangle and I found the perpendicular bisector of all three of those sides, and this time they're meeting way out here. It's not even in or on the triangle. So for an obtuse triangle, when you draw and you find the circumcenter, P is outside the triangle. So this will be helpful for a lot of the work that we're doing later. So come to class with any questions that you have. I know it was a lot, but we're going to have a lot of fun when we come to class.